Hello everyone. Welcome to this webinar which is on modeling human exoskeleton interaction with AnyBody. This is a joint event between Aalborg University and AnyBody Technology. We appreciate your time and hope that by the end of this webinar we have successfully introduced and discussed a few concepts and techniques for what's called in silico modeling and simulation of exoskeletons using AnyBody modeling system. For this presentation, you're going to see an introduction to AnyBody modeling system by me. So my name is Mohammad Sharif Shurije. I'm an R&D engineer here at AnyBody Technology. I'm hosting this webinar with my colleague Dr. Monkey Jong, who is a senior application engineer here at the company. Then we're going to have the main presentation by John Rasmussen, who is a professor here at Aalborg University, and then we're going to have some final words by me, and then we're going to move on to the questions and answers. AnyBody modeling system is a software that does multi-body kinematics and dynamics analysis of human-centered simulations. The software comes with AnyBody Managed Model Repository, or AMMR, which includes many application examples, as well as open body model. Essentially, AMMR is a collection of generic musculoskeletal models that are developed and contributed by researchers around the world. So if your application is one of those that are already in the AMMR, you just need to minimally change that model to adapt it to your data. Otherwise, you can start from those open body models and develop your own model with your desired entities and assumptions. AnyBody software has somehow unique simulation features that I'd like to highlight here. The first one is man-machine interaction simulation using our user-friendly SolidWorks to AnyBody import toolbox. So essentially, you can convert your SolidWorks model to AnyBody entities and scripts. So if you're familiar with the terms in SolidWorks, for example, mates and parts will become automatically rigid body joints and rigid body segments. The second feature is reaction force prediction. So there is a tool in AnyBody that, for example, if there have been some external forces on the human subject that you couldn't measure for any reasons, AnyBody can predict those forces for you. So this tool can be used, for example, for the forces at the straps of an exoskeleton. So currently there are no cheap sensor that can measure three-dimensional distributed forces at the straps. And the last specific feature that I'd like to highlight is you can do subject-specific morphing of the bones in AnyBody based on medical images. This slide explains the principles of doing a dynamic analysis in AnyBody briefly. So essentially, for inverse dynamics, we need motion and external forces and external moments as inputs to the model. Of course, as I mentioned earlier, AnyBody users can have an option to predict the ground or in general reaction forces as well. So if the external forces, which are the ground reaction forces, are not measured, those can be predicted in AnyBody. Also, some kinematics can be decided and estimated by the AnyBody software. Then, once those inputs are decided or specified using the muscle recruitment optimization solver with various options of objective functions, AnyBody calculates the internal musculoskeletal variables such as muscle forces, muscle activity levels, joint reaction forces that include the muscle forces, and many other variables like metabolic energy and power. If you have a detailed CAD model of a mechanism or a machine, such as a gravity compensation mechanism for the exoskeletons, for example, so then you can easily import them into AnyBody. So like you mentioned before, SolidWorks parts and mates will be automatically converted to rigid body segments and joints with no excessive or further effort. Subject-specific data such as anthropometrics and medical images will be used to scale the generic model that will join the CAD model and will be run for the specified activity of daily living. AnyBody system is capable of being interfaced with finite element analysis for more local deformation or stress-strain analysis. Before, during, and after AnyBody simulations, you can use programming interface for more scripting or, for example, running control algorithms or an outer loop of optimization around AnyBody simulations. Okay, so with this, I'd like to pass the word to John, who will talk about the presentation, the main presentation, which is on interaction of exoskeletons and musculoskeletal system using AnyBody.
Thank you very much, Mohammed. As Mohammed said, my name is John Rasmussen, and I'm a professor of biomechanics at Aalborg University, which is neighboring AnyBody Technology. I'd like to thank AnyBody Technology for this opportunity to come and talk about exoskeleton design using musculoskeletal simulation. It might not be entirely clear to everybody exactly how this type of analysis can contribute to the design of exoskeletons. Except that there's obviously a human inside an exoskeleton, so there is some sort of biomechanics going on in there. But let's try to look in a bit more detail on how musculoskeletal simulation can benefit the design process of exoskeletons. So I'll first go through the exoskeleton design phases, and while doing that, actually, I will present some examples. And obviously, at the end, we'll arrive at conclusions, just like normal for this type of presentations. So the way I see exoskeleton design phases is just like designing any other product, actually. So you imagine that when you're designing some sort of product, you are going through a sequence of processes where you begin with conceptual design. So you're kind of coming up with ideas, general ideas for how the product is going to work. And then gradually the designs become more detailed, and you go from the conceptual design to the detailed design phase. However, and it's also like that with exoskeleton design, but there is an additional design phase that I think comes before the actual design of the exoskeleton, and that is what we can call the baseline analysis. So that's the biomechanical analysis of the working situation that you want the exoskeleton to be helpful with. So this is very important for a number of reasons. First of all, to know what the exoskeleton is actually going to do, and also more precisely what parts of the body and what situations it's going to work in. But also, and that's what the name baseline indicates, you need something to allow you to compare the situation before and after the exoskeleton, so that you can see the possible benefit that the exoskeleton is making, and also so that you can see possible problems that the exoskeleton might be causing. I will get back to that in more detail a little bit later. But you see the three situations are the ones that are shown here with the three images. So in this case, the working task is lifting a box. And we have the situation without the exoskeleton here on the left-hand side. You can see that the elbow flexors are quite red in this picture, meaning that they are highly loaded. And so possibly on the middle picture with the in the conceptual design phase, we would be adding some assistive moments to that, and you can see we have done that, and now the muscles in the elbows are not as red as they were before. And then if we figure out that that's a good idea, maybe we want to create an exoskeleton that does exactly that, which is indicated on the right-hand side. It's not always as simple as we have indicated here, because in reality, degrees of freedom are coupling and motions, and rather than static postures are what we are targeting. And also things tend to interact a lot in biomechanics. So let's look in a bit more into detail on how this is done. So the first part, as I said, is the analysis of the working situation. And now you can see that we have an animation over here on the right-hand side indicating that normally the working situation would be a motion, possibly or usually even much more complicated than the one that you see over on the right-hand side. So we need some basic information about how this working process is going on. And with the analysis model, we can then figure out which time frames of the motion are the critical ones, which are the times in the motion or the postures in the motion that are causing high loads on the different body parts, and also which are the different body parts that are actually highly loaded and have to be assisted by the exoskeleton. So this is the baseline analysis, and it has a very important function. There's a couple of different scenarios for baseline models. The first classes of scenarios, they have to do with whether we have kinematic data for the motion. So imagine we have some sort of working task that we need to do, and maybe we are lucky, which is what we have tried to indicate in the video I'm highlighting here. So maybe we are lucky that somebody or ourselves have been doing motion capture analysis of this working situation. So that's what you can see here in the video indicated by the dots on the model here. So those are optical markers from a motion capture system. And we have imported those motions into AnyBody. And that way we can very accurately replicate the motion of the working task. So that's a good scenario. But unfortunately, that very often it's not the case. So very often it's difficult to do the motion capture. Maybe you haven't got the equipment. Maybe the place that the working task is taking place doesn't allow for motion capture. You know, there can be many other issues or reasons why you don't have motion capture. Maybe you don't know exactly how the motion is being performed. Or maybe even the motion is not possible without the exoskeleton, and in that case you can't actually do it without the exoskeleton. So there can be many different reasons. And if that is the case, then you have to try to predict how the motion is taking place without actually having the motion in the first place. And that's what we are showing over here on the second picture. So it is actually possible with the kind of musculoskeletal simulation that's taking place in AnyBody to some extent to predict motions. And that happens in two different cases. One case is the one that is illustrated on the video here. And that is when you have environment constraints that are determining so much of the motion that there isn't that many degrees of freedom left for the human. And so the example over here on the right-hand side, you can see this is a person closing a gate. Could be the tailgate of a car. It could be any other type of gate that the person is closing, and in this case the hand is connected to the gate, and the gate has to move in a certain way because it's hinged at the top, and that means actually that there are many degrees of freedom of this system that are already predetermined. AnyBody has a simple way of predicting what the other degrees of freedom, how the other degrees of freedom will move in that situation. And the movement might not be exactly the one that a person would choose to do, but it will be pretty close. As you can see here, it's not an unnatural motion that we get in this case. So to some extent we can actually do posture and motion prediction with technology like AnyBody. The other way that we might work is by motion keyframes. So imagine that you're standing in the workplace that you're interested in, and you can you know that the working situation requires your different end effectors, hands and feet and whatever, to be at certain points at certain times. And if that is the case, then we have keyframe postures. And we can then measure where those points are in space, and we can subsequently generate keyframes in the model in AnyBody, and then we can make AnyBody interpolate between those keyframes. And then again, you will have a rough estimate of the motion generated that you can subsequently analyze. So let's go to the next slide, and look at two scenarios for external forces. Because as Mohammed said, the analysis is inverse dynamics. So in principle, we put the external forces into the model, and then the model is going to predict the internal forces. And again, we have the good situation up here in the video at the top. I'm just going to highlight that here for you. And that's a situation where we have force platforms that are measuring the forces between the environment and the human body. In this case, we only need force platforms because the ground is the only place that the body is touching the environment. Of course, in a working situation, the hands would often be touching the environment too. And in that case, we would need force dynamometers or something like that, which could measure the forces that we're exerting on the environment. Very often it's not the case. Very often we don't have those types of measurements. So we have to estimate what those reaction forces are by other means. And fortunately, that is actually possible. Take a look at the video up here at the top, where you can see I can highlight that one, where you can see a model that's performing some operation with stick. It could be washing windows or something like that. And you can see under the feet of this model, you can actually see the ground reaction forces being estimated by the system, by the technology. And this is a simple matter of dynamic equilibrium. So if the guy is standing on the floor and gravity is acting on him, and also he is moving, so there are certain inertia forces acting on him as well, then these inertia forces have to be transferred to the environment. And AnyBody has ways of calculating what they are, because it has a fully dynamic representation of the motions in the model. You see two other cases of the same below. You see here a chair that's rocking from side to side, and you can see the blue arrows coming out of the model are the computed reaction forces between the human and the chair. And then you see down here at the bottom, you see this exercise machine, this elliptical trainer. And if you look carefully, I'm sorry, the image is quite small, but if you look carefully, you see the same types of blue arrows coming out of the feet of this guy, and those are the reaction forces that are calculated by the system between the feet and the foot plates. So it is actually possible in most cases also to estimate the environment forces if we don't know them already, just like it's possible in most cases to come up with predictions of the motions. So that's how we create our baseline models. So the conclusions on those baseline models is that this requires some information about the motions, the overall motion, and what we get then subsequently is we get all information about the motions of every part in the body. And we also get all the joint forces computed, say including critical points like spinal compression forces or shoulder forces or those types of places that are prone to injury. We also get muscle exertion levels for all of the body parts, so we can identify whether the working situation puts the most load on the arms or the hands or the shoulders or the legs or whatever. We can also calculate metabolism for single muscles and the entire muscle system, and I'm going to show an example of that a little bit later. So let's continue on to the second stage, which is what we call the pre-prototyping or conceptual design stage. So in this stage we are not yet designing the exoskeleton in detail, but we're just thinking about what the tasks that the exoskeleton would do, what they would be, and how we can realize them. So let's go back to the example that I showed you before with the box lifting and the realization that in this case we need to add some assistive flexion moment to the elbows because the elbow flexors were very highly loaded in the baseline model. So in the picture, in the image you see here, we have added some assistive moment, and you can see that this has caused a reduced activity in the elbow muscles, in the elbow flexor muscles. But that might not be all, because if we look carefully, we can see that there are other parts of the body that are highly loaded. We can see some muscles around the shoulder are highly loaded, and if we turn the model around, we would also be able to see that some of the muscles in the spine are highly loaded. So if we were constructing an exoskeleton, we would probably have to do something with the exoskeleton that will also relieve those other parts of the body. And now in the conceptual design stage, we can start thinking about what would the simplest way of accomplishing all of these tasks at the same time, what would that be? So would we have to make actuators for the elbows and actuators for the shoulder, actuators for the spine, and maybe also actuators for the hips, because there's also hip flexion involved here, or hip extension, sorry. So would we have to make individual actuators for all of those parts, or could we come up actually with a system that would in one go would relieve all of those different or serve all of those different purposes? And the answer is yeah, I think so. If we think a little bit about it, we can possibly do something like this, which you see on the screen now. So this would be a kind of system that would, if this blue cable that you see here, if this is in tension, then it will provide elbow flexion, and shoulder flexion, and spine extension, and hip extension all at the same time. So with one actuator, you would actually be able, if the moment arms about those different joints, if those moment arms are properly tuned, you would actually, with a single actuator, be able to relieve many of the joints that this working process is loading. And with AnyBody, of course, you can apply a conceptual device like this, and you can see whether it has the intended effect on the different joints, and you can also see whether you have some side effects. Possible side effects for this one might be that if there's tension in this guy here, then maybe the tension over here on the back, which I'm highlighting here, this tension would work to compress the back, and maybe this would increase the compression of the spinal vertebrae, and of course it has all its own set of injuries that can come from that. So so now we're into looking into different types of conceptual designs and what possible consequences they can have on the body, positive and negative. I want to show you an example of how this was done, and this is actually done by Mohammed, who was speaking to you just before, and was presented at a conference very recently, the WeRob conference. And this is kind of a very nominal way of doing things. Let us imagine that we have again a lifting task like we were looking at before, and in this lifting task we want to look at the influence of assistive moments in the ankle and in the knee and in the hip, and we would be interested in how much assistive moment would be necessary, and also is the effect of this assistive moment, is it bigger on some of the joints than it is on others? So is it more important to relieve some body parts than others? And what we're going to do here is we're going to use the metabolic power exerted by the muscles as a design criterion. So we're going to compute the metabolic power, and we're thinking that if there's a lot of metabolic power involved, then probably the worker will perceive the motion as very strenuous. So the goal of the exoskeleton design here is to reduce the metabolic power. We're also designing these torque providers. We're actually designing them just as springs. So we have some for each joint. We have a reference angle, and then we have the actual joint angle. These are calculated by the system all the time. And then we multiply on that a spring constant. So what we have here is actually a torsional spring that we can apply to each of the joints. And this, the spring moment that it's providing is then a linear function of the joint angle, so this actually becomes a spring. So three cases, we're looking first at the ankle, then we look at the knee, and then we look at the hip flexion. So the way we do it is we just add the spring in the system, in the first case to the ankle, and we let the spring constant K, we let this vary in steps of 50 Newton meters per radian between -300 and plus 300. So the spring can kind of work in both directions, whatever it is that we need. And then we look at the total metabolic power over the motion. Of course, we can integrate this up and find the metabolic energy if we like that. And we do this in a parameter study. So we just let this value vary systematically, and then we record all of the metabolic power curves. And you can see that for the ankle over here, there is a distinct minimum, which is the red one. But you can also see that it's not that much different from all of the other ones, maybe because there isn't actually that much motion in the ankle during the process. So if we do the same, say for the knee, then we get a much more pronounced result. You can see here that there's much more difference between the metabolic curves depending on what stiffness we use of the spring in the knee. And you can see that there's now a very distinct one that has the lowest integral, which is the red one that we see here at the bottom. And similarly, if we do exactly the same thing for the hip, we also get a rather pronounced results, even more actually, where you can see that the optimum spring of 100 Newton meters per radian is really much better than a lot of the other ones. So it looks like at the hip and at the knee, there's a lot of potential for reducing the metabolism of the worker by adding a spring to those joints. So this is something to think about if you're designing an exoskeleton for a lifting task. Remember, springs do not need any energy input, so this actually comes entirely for free. So this is an example of how you can do a conceptual design study in which you can get inspiration for how to actually build your detailed exoskeleton. And that brings us, of course, to the second part of the design phase, which is the detailed design. And the first thing we can notice is that, of course, detailed design of an industrial product like an exoskeleton, of course, does not take place in AnyBody. It takes place in a CAD system. So what we have done is we have equipped AnyBody with an interface to SolidWorks, so that your SolidWorks assemblies, in SolidWorks, mechanisms are made as assemblies, and these assemblies can be exported from SolidWorks and imported into AnyBody. And so the degrees of freedom in the assembly also become motion capabilities of the mechanism inside AnyBody. So we export the geometry, and we export the kinematic constraints. We also export surface properties and colors and stuff like that, so that the models that you get into AnyBody look really nice. So that way you can take you can couple your biomechanical or musculoskeletal analysis with the design process that's taking place in the CAD system in a very easy way. So let's consider what it is that we want to do in this stage of the analysis. So remember that now we have done the conceptual analysis before, so we have a pretty good idea about what the exoskeleton is supposed to do. And now we just have to design the details of this exoskeleton. So what are the issues now? So we can split the issues up into kinematics and kinetics. And among the kinematics issues are kinematic compatibility. And I'll talk about that in just a second, so I won't go much into that now. It's also the possibility of collisions between the exoskeleton and the human body. And it is also a simple thing like figuring out what actually has to be the range of motion of the actuators in the model. Of course, if the actuators turn out to have not enough range of motion, then you will end up with an exoskeleton that actually constrains the motion that people can do. You probably don't want to do that. On the kinetic side, it's particularly the contact forces between the exoskeleton and the human that are important. You might want to make a very strong exoskeleton that might allow people to lift very heavy things. But that probably also means that the exoskeleton has to transfer very large contact forces to the human body, and this might not be comfortable or even dangerous. And we can figure out with AnyBody what those contact forces are. You can also calculate power consumption and peak powers for the actuators. This is important for dimensioning batteries and also the actuators themselves. Similarly, with peak forces or moments of the actuators. And finally, as we saw before, we can compute metabolic energy and those kinds of things depending on the design of the exoskeleton. Let's take a look at a couple of examples. This one I borrowed from my colleague, Professor Xiaoping Bai. He is working at my department at Aalborg University, and he is heading European research project called Exosuit, and you see down here at the bottom, you see the web address, the URL for that project, so you can go and check it out after the presentation here. I want you to pay attention to the image over here on the left. So this is an exoskeleton for the upper limb, obviously. And what I want you to notice is that this exoskeleton is connected to the human body, and it is actually a parallel mechanism. So it's like you have an extra arm running next to your real arm. So these become two parallel mechanisms, and they form a closed loop. So if you're supposed to be able to move with that exoskeleton on, then you cannot have kinematic incompatibility between the exoskeleton and the human body. And this requires both tailoring the way the exoskeleton is connected to the human body so that there's the necessary degrees of freedom, and also figuring out how to make the joints of the exoskeleton. Consider the human shoulder, for instance. It's a very complicated joint. You have the glenohumeral joint here with the humerus and the scapula. That's like a loose spherical joint. But then in addition, you have the whole shoulder girdle, which can move as well. And so the exoskeleton has to accommodate all of those complicated motions in order not to constrain the user more than helping the user. And so when you start building up your exoskeleton, you can then investigate all of these different issues with the AnyBody model, and you can figure out what are the contact forces that are exerted and things like that. I want to talk a little bit about the contact forces, because one important element in the contact forces is the ability to model contact properly. So contact, as you probably know, is a very nonlinear mechanical thing when we talk about unilateral contact, and that is also the case with exoskeletons. So the contact forces of the exoskeleton are going to shift from one side of the body to the other, typically when the exoskeleton is exerting forces in different directions. And obviously we have to model that properly. We have to model the actual contact forces on the skin of the user. And this requires proper contact elements that are unilateral and which can also take friction forces into account. And we can do precisely that in AnyBody, and the video here is actually showing that. So all of those blue arrows coming out of the video here, you can see that some of them are perpendicular to the body and some of them are parallel to the segments. The perpendicular ones are, of course, the pressure forces, and the parallel ones are obviously the friction forces. The way we model that in AnyBody is by means of the same types of algorithms that we use for the muscle recruitment, and so since those algorithms are already in AnyBody and are very efficient, it means that you're not adding a whole lot of layers of complexity from a mathematical point of view to the model when you define these contact points. So AnyBody actually handles those very, very effectively. Here's another example of those types of contact forces where you see the perpendicular forces and the parallel forces here, the parallel friction forces over here on the side. So I won't go more into that at the moment. Instead, I want to come to the conclusions. So the human body, the biomechanics of the human body is very complicated, and this means that when you are designing an exoskeleton, you are designing something that is supposed to assist a system which is already very complicated. And this of course gives you some additional challenges, because the exoskeleton has to cope with the complexity of the human, but also the consequences of what the exoskeleton does can sometimes be very difficult to understand. So exoskeletons can help the human, and they can enhance safety and performance and so on by taking some of the loads that would otherwise fall on the human. But they can also cause discomfort or pain or even injury if you make the exoskeleton such that it allows the user to put loads on the parts of the body that are not supported by the exoskeleton. So being able to understand all of these things and how the exoskeleton influences the human body, I really think it's very difficult to do that without having a comprehensive biomechanical model to support you. And this is what we can do with the type of models I've shown today. It's also important to understand that the musculoskeletal simulation can actually assist in several stages of the design phase, and maybe even more so in the beginning phases, in the conceptual phases. You know that many of the decisions you make in the conceptual phase are going to decide the quality and the cost of the exoskeleton in the end, further down the line. So it's very important to start off in your design work in the right way, in the right direction, because otherwise you will end up, after you have done the detailed design, with a solution that probably isn't very good. So with that, I'd like to thank you very much for your attention, and I will pass the mic back to our host, Mohammed.
Okay, thanks very much, John, for the very nice presentation. Personally, I really like the idea of categorizing exoskeleton design into actually 3 phases: baseline, as you mentioned, conceptual, and detailed design. So I think this might be very inspiring for the exo designers and how they can study the influence of the exoskeleton on the human body. A little bit of general information. So please stay tuned to our website, anybodytech.com. So I think there might be 1 or 2 more webcasts by the end of 2016 for your interest. And also, if you're interested to see the list of previous webcasts, we have a long list of recorded webcasts that you can see under our website or in our YouTube channel, AnyBody Technology. We recently had a joint event with Wearable Robotics Association, WERA, which was on modeling and simulation of wearable robots. That also might be interesting for those of you who are working on the exoskeleton field. If you go to our website, you're going to see links for downloading the software, requesting trial licenses, and the list of publications, including the publications on the exoskeleton area. And with that, so I'd like to thank the funding agency. So part of the slides and the project was done through the MOVE8. It's a European Horizon 2020 project, and you can visit the website for more information on that. So I think now it's time for questions. I've received several questions that I'm just trying to sort them. Okay, so let me start with this, John. Regarding reaction forces, if I want to simulate one of the hands of the mannequin to hold on to a rigid frame for supporting himself, do I need to model the frame as well? Would placing the hand in the posture and using any react force or any reaction force be sufficient?
Thank you. Yeah, that's a good question. I think the concept of an any react force might not make sense to people in the audience who don't know anybody, but an any react force is a way of modeling supports in anybody in an abstract fashion, and the person asking the question is quite right, that let's say you were holding on to a rail or a handle, supportive handle or something like that, you don't actually have to model the handle. You can place the hand at the position where you imagine the handle would be, and then you can create an any react force which would actually tie the hand to that position in space and provide the necessary or the resulting reaction forces. These reaction forces would influence balance and muscle recruitment and possibly also the forces that the exoskeleton has to provide. That will come automatically out of the equilibrium equations.
Okay, thanks. So let's go to the next questions. How do we calculate the total metabolic power?
Yeah, so the current versions of AnyBody have in them an opportunity to calculate the metabolism of every muscle. So whenever you do an analysis, you can browse your way into the muscle, and you can get information about the metabolic power of the muscle at any time instant in the analysis. New versions that are coming out of AnyBody have a much improved metabolism model that we implemented recently, and but it still works the same way. So if you want to have the total metabolic power for the entire body, then all you have to do is you simply sum up all of the muscle metabolisms, and then you get the number for the entire body.
Okay, thanks. So the next question is, how do we define contact force between the exoskeleton and human?
Oh yeah, yeah, that's kind of technical. So as I mentioned, the contact force is a unilateral force, and if you know about mechanical analysis, you know that unilateral forces or contact forces usually complicate analysis problems a lot, because they introduce a nonlinear component into the analysis problem. It's not exactly like that in AnyBody, because everything in AnyBody is already very nonlinear, so it doesn't really complicate things further in that respect. But the way we model it is that we actually model the contacts using the same algorithms that we use for the muscle recruitment. You see, the muscles have many properties in common with contact, in the sense that muscles are also unilateral. So muscles can only pull, where contacts can typically only push. Mathematically, this becomes the same thing. So we have defined these contact elements that are available in the model repository. There's a little, the definition of them is kind of complicated. So we have made objects available that you can just insert into your models, which are a part of the model repository. And so when you insert these objects into your models, you can define contact elements between the body and the environment, or between the body and the exoskeleton, or between any two surfaces that you want. And the resulting contact is then solved the same way that the muscle recruitment is handled in AnyBody. So it doesn't actually add much to the computation time, not more than an additional muscle in the model would. And furthermore, so when contact is available, like say, if we imagine the first question of say supporting yourself on a rail, if you do something like that, then the contact forces or reaction forces, whatever they are, they go into the whole equilibrium system of the body, and they influence the recruitment of muscles in such a way that equilibrium is still fulfilled. So if the contact is useful, then probably the voluntary muscle or the voluntary actions of our muscles is going to use the opportunity, and the algorithm actually reflects that. You can imagine one of the things I sometimes tell my students when I want to explain how it is. You can imagine that you're standing up against the wall, but you're not touching the wall. So you're just standing right next to the wall. If you stand there for a little while, you will be inclined at some point to lean against the wall. So it doesn't change your posture much, but it changes the equilibrium of your body. And the contact elements in AnyBody actually work the same way. So when contact is possible, the system is exploiting the contact. I hope that answers the question.
Okay, thanks very much. We have received many questions, but I think we're going to have time maybe for more, one or two questions. Okay, so here's one. In AnyBody, I see to simulate the motion of any activity. The problem here is how to create the initial state of the motion which one to simulate. I think that was in the question form. So I think the question is asking about the initial state or the initial condition of the motion.
Yeah. So it depends a little bit on which situation we're talking about. So maybe you remember that we talked about two situations. One was where we had motion capture data available, and the other one was where we generated the motion kind of on the fly using either kinematic constraints or keyframes. So if we're using mocap data, I don't think that's what you're asking actually, but I just want to cover that as well. If you're using mocap data, then our mocap models, they have ways of putting the model close to where the mocap markers are. Sometimes it's necessary with a little bit of manual intervention to define the initial posture so that the body is close to the mocap markers. But after that, everything is automatic. But I sense that the question being asked is actually about the keyframe definition of motions, or possibly the one where we use the kinematic constraints to define the motions. Well, if we're talking about keyframe motions, then actually the way you go about that is that you typically take one of the existing models in the library, the one that's called the standing model, for instance, which you can control the posture of that through the anatomical angles. So you can simply there's a place where you can specify what the anatomical angles are. And so you would just by trial and error, you would specify the anatomical angles that correspond to your keyframe postures. It takes a little bit of experimentation, but it's not very difficult. You just change a number and you look on the screen what that means. I mean, what kind of posture do you get now, and then you change it a little more, and then you have maybe the keyframe that you're looking for. Then you take note of what those postures are in terms of the joint angles for the different keyframes. And then you create interpolation drivers that will interpolate the same joint angles between the same postures, and that's actually all that you have to do to make to model the keyframe motion. There's also some other ways that you can do it. You can let's say you have an end effector like a hand that you want to go through a certain path. Then you can actually define an interpolation driver which would be a sequence of points that the hand would have to reach. And when you add that as a driver to the model, then that's what the hand is going to do, because the existing drivers in the standing model, for instance, are soft drivers. So you don't have to disable those. And so when you specify that the hand has to go through a certain sequence of postures, then all of the other constraints or drivers in the model, they will accommodate the hand doing this, because all of the other constraints are soft constraints. So they will be compliant with whatever you specify in addition to themselves.
Okay, thanks very much. So I think we have to close the event. Thanks very much again, Professor John Rasmussen. Very interesting and nice talk. And thanks very much again for everyone for attending this webinar. Please stay tuned for our future webinars. And then the recording of this webinar will be emailed to you. And regarding the questions, I know there were several questions that were left unanswered. So we try to get back to you in a few days with answers and maybe discussion. So just feel free to email us back if you feel that you're not convinced with our answers, or if you have any questions. Thanks very much again, and I wish you a pleasant day wherever in the world you are. Thanks and bye.